Now let's talk about clever Matlab. If you have forgotten everything out of that lecture, let's say in 5 or 10 years, then I instantly want that you did not forget what I'm talking about now. I'm talking about clever Matlab, and we will have in every section a subsection clever Matlab, and I show you to produce nonsense answers using the real Matlab. Matlab is not for free. You will be charged 1,000 euro that you are allowed to use. So it's a really professional programming language, and many people like to use, and they like so much that they say, okay, it's worth 1,000 euro. And now I want to produce silly results. And here you can see a very silly result. We will have a matrix A, and we will have a right-hand side B here. And then we will calculate the solution A times what is B, and we can do that using that command. That is the command A \B. Give me the solution. A is a square matrix, B is a vector of the size corresponding to A, and then give me the vector X, which is the solution of A times what is B. And doing so, we will get a result X, and knowing the correct solution XL, we can subtract the solution which is correct and subtract the solution we calculated. Then let's take the absolute value and let's look for the entry with the largest value. And then we get a 1.8245, and in this situation again, all the answers in X are numbers between 0 and 1, and we are able to produce nonsense answers out of Matlab. And what do? We do what we already did. We are taking a large matrix A, and then in this matrix, and here in that block, we are using numbers which are very close to 0. Let's assume that there's a real life problem, and this real life problem leads to a matrix A, and here all over are entries between 0 and 1, uniformly distributed. But in that block here, top left, there are entries which are very close to 0 but not completely 0. Let's assume that there is a real life problem of that time. So here we introduce that situation. Let's have very small numbers on the top left block. And then let's produce the solution vector. It's a very academic situation. We construct a coefficient matrix in that way. Normally coefficient matrices are not being constructed by a mathematician, but are coming out of a problem. Okay, let's have this to be the solution, and then let's find the right hand side. And now we know the solution XL, and now let's find out what does our algorithm give us. Okay, and before doing so, we multiply the first 10 lines of the coefficient matrix with a large number, which compensates for that. And let's also adjust B, and that means that the solution XL will keep being what it was before, because we multiplied the whole equation by 2 to the power of 50. So now let's ask our LU decomposition simple. We already did. Let's ask our column pivoting algorithm, and then let's ask our total pivoting algorithm. And what do we see? We see very silly results here, and we see a little improvement here for column pivoting, but deviations of 34 are still catastrophe. So the answer is completely nonsense, which we got by using that algorithm. But when we use total pivoting, the problems are healed completely. So we have very, very good result X, which we found out here, and it's very, very close to the really correct solution XL. And now we are calling the real Matlab. This is the command you will use if you are doing Matlab. Having Matlab, having paid 1,000 euro for, you don't have to implement how to solve systems of linear equation. That is still implemented in Matlab, and normally I will always use the Matlab command. I don't have to use my algorithms, and we talked about that because if you're using Matlab, then you have a feeling, you know what's going on in Matlab internally. And now you see the following: Matlab produces the same nonsense results. If you ask Matlab type and then the name of the algorithm, then you can see the code, what's running inside, and then you see Matlab also uses column pivoting. And I'm not really sure why Matlab is more clever than we were here. If you want, you can analyze that, but it's still the same. If you have deviations of 6,000 and then you have an algorithm producing deviations of 34, then 34 is still a catastrophe. And having deviations of 1.8 is also still a catastrophe. So the Matlab answer here is complete nonsense. And if this was the typical situation here, then that would mean that Matlab is not worth a single penny. So Matlab does use column pivoting and it does not use total pivoting, although total pivoting will heal problems which column pivoting will not heal. So I was very, very surprised about that fact. Why is that true? Why does Matlab does not use total pivoting? This would be a remedy. Why is Matlab so stupid? The point is that Matlab wants to be fast, and total pivoting means approximately 20 or 30% extra time, which you almost never need. So almost never there is a disadvantage using column pivoting, and that means that if you are using total pivoting, more time having no advantage. And that's the case why the makers of Matlab decided not to use total pivoting. You can be 100% sure that they know the mathematics, they know column pivoting, they also know total pivoting, but they decided we use only column pivoting. As I said, I was very surprised that that is true, but when I was the programmer, I also want to be fast, and true is there is not a single application where total pivoting is necessary and column pivoting is not enough compared to that. There is not one single situation in real life, and so this is a really academic idea to have problems like that here. And so the makers of Matlab decided it that way, and so never forget that section. It's entertaining, it's educating, and it's interesting.